All right. Hi, everyone. Good morning. Thanks for making it to the session. Probably looking at the title, you would think that this is kind of Texan slang to it, but don't presume I'm from Texas. Let me take this opportunity to introduce myself. My name is Krishna Harsha Voora. I work as a software developer in IBM Software India Development Labs. In this role, I primarily help ISVs or independent software vendors and business partners and move them to Linux on Power ecosystem by doing validation and benchmarking exercises. And I also evangelize blockchain as a technology at various forums, meetups, and conferences. My colleague Mithun HR, who couldn't make it here to the summit, is a technical enablement specialist or a consultant. He also works on enabling ISVs and business partners onto Linux on Power ecosystem. Taking a quick look at the glimpse at how we are going to spend the next 30 to 40 minutes, I will be touch basing on a few of the focus areas that I'll be talking through today. One of them is IBM and Red Hat partnership. This has nothing to do with the acquisition or merger that happened. I'm just going to touch base on how, in the open source world, how beautiful things IBM and Red Hat have done together to benefit then customers. I'll touch base on the overview of OpenShift, which is Red Hat's product, and then different use cases or workloads that could be targeted to run on OpenShift. And then probably I'll give you a brief introduction on Power 9 processor family, and I'll spend considerable amount of time on the objective and the workload that we have picked up for this particular performance case study. And if time permits, I'll show you a CAN demo wherein I'll be spinning up one application on top of OpenShift and try to simulate some workload on top of it. IBM and Red Hat have coexisted in the open source world for near about 20 years, and they have done marvelous jobs. And then they have pretty huge product portfolios as a part of their charter. IBM Power Systems, in particular, has worked with Red Hat to bring most of its current capabilities or product portfolios onto Power. Speaking about Red Hat Enterprise Linux, which has been running on top of Power System from a long time. And then a few others, like we have had Red Hat OpenStack, we have had Red Hat OpenShift, which are now part of IBM platform as well. I would like to take some time and talk about the cloud workloads over here. We know that half of the workloads which run on cloud today work on top of Linux operating system. And Red Hat is indisputably the #1 cloud distributor in terms of, and then also Linux distributor and support provider over here. There is an imminent threat when an enterprise Linux running, an enterprise application running on top of multiple clouds run into vendor lock-in kind of an issue. IBM and Red Hat have worked with end-to-end solutions which helps unify your public and private cloud investments, and then that makes use of your application and services built around open source frameworks, and then which helps eliminate the vendor lock-in as we speak. The reason I say we can eliminate the vendor lock-in is, let's assume you have an application running along with a software bundle which has not been signed and you're running it on top of a production, and all of a sudden they pull their support back. What do we do next? We have an application running in production. To eliminate that, IBM and, in fact, Red Hat OpenShift has a catalog in which they have huge suite of softwares being signed and securely published to an in-house repository kind of a thing, which could be plugged, which could be pulled in onto your OpenShift instantaneously, and you can run on top of your Power Systems too. There are limitless applications one could only realize with one understands the capabilities of OpenStack or OpenShift as such. Boiling down, there are 3 focus areas that I'm going to touch base on, and they are fit to run OpenShift on Power as such. One of them is application modernization story. Let me give you a brief analogy on how application modernization story can work over here. an enterprise company running your application depending on your legacy software, and then you realize you want to shift to the microservices-based approach, and you don't know where to start and how to start it. You could probably leverage OpenShift as it is, because it has a whole suite of offerings within it. You just have to download them and then get started with your application development as such. With microservices-based approach, whenever you try upgrading one of the components, you're not entirely compromising on the availability of your application as it is. And also, this helps in terms of application modernization story. And then when it comes to building new data-centric cloud kind of an application, the data at which it is bursting in terms of exponential growth, we need to rethink the way the cloud internal organizations works. Because the future clouds will need to have, will be capturing, processing, and analyzing the logs in particular, right? So we need to bring the compute to the data in turn, as opposed to the traditional approach of bringing the data to the compute. So wherein we need to have multi-cloud kind of a scenario, and then OpenShift provides a cloud-like experience which could be leveraged easily and then seamlessly and deploy your applications on top of it. We have had a lot of traction around machine learning and deep learning. How could you get benefited with Red Hat OpenShift? It provides you an inbuilt plugin that could be leveraged, and then you can run your model on top of your GPUs directly. From IBM Power 9 processor family, we have an offering called AC922, which is built for AI kind of a workload. It has its planar surface aligned in such a way that you can pump in your data from CPU to GPU, instantly making use of, and pretty bulkily, in fact, making use of PCI Gen 4 kind of a buses. I'll talk a little deep into it a little later. So this is the Power 9 family I was talking about earlier. If we categorize this slide into two halves, the vertical halves, one of them is LC922 kind of a box, and all of these are based on Power 9 family. So the LC922 box is majorly based on big data kind of a workload. You could target your big data kind of workload on this box. And then we have had the AC922, which is a Lego building block of your one of the supercomputers as of last year, 2018, which is Summit and Coral. This, as I was mentioning, the planar surface is aligned in such a way that you can pump in a lot of data from your CPU to your GPUs, and it comes with pretty good support from the software aspect of it. We have LMS, which means large model processing. You could process your high-resolution pictures on top of your GPUs directly without overshooting its memory capabilities. And then moving on to the right side of the slide, we have had IBM DB2 and Oracle, which are enterprise kind of workloads that could be easily run on your E950 and E980 kind of boxes. And then moving on to the middle segment of the slide, which is SAP HANA kind of a workload could be targeted on this, because we have had a huge footprint requirement when we need to run SAP HANA kind of a thing on top of it. IBM Power 9 processor family has a huge footprint, and then we have released specifically a tailor-made kind of a server, which is S922 and S914 and S924, which caters to the needs of SAP kind of workload. So now that we know what kind of workloads should be targeted for OpenShift, we need to know what kind of infrastructure also should be targeted when it comes down to running OpenShift on top of Power in order to get much of a benefit to your end consumers or customers. There are different modes. When I say modes, there are different hypervisors available in market that could be leveraged in order to run your systems. One of them is the KVM approach, which is the industry standard virtualization hypervisors are kind of a software. You can run LC922, which is our big data kind of a workload on top of it. You can run it either in bare metal and or in hypervised or in a virtualized hypervisor kind of thing. We have had AC922 where you can run your AI kind of a workload in bare metal mode. And then we have the traditional Power VM partitioning hypervisor, which is used for majorly targeting your enterprise kind of workloads. So the whole premise of this slide is to understand you could run OpenShift on any kind of mode, let it be KVM, let it be Power KVM, or Power VM. So I would like to spend a considerable amount of time on the choice of workload that we have taken. For this particular performance case study, the workload is pretty data intensive. The reason we picked up this kind of workload was to put a lot of pressure on top of put a lot of performance workload on top of your CPUs and see how Power 9 processor stands out as compared to the Skylake in this particular performance study. The objective when we were doing this performance case study was to derive a price performance advantage that we could have as a leverage on when we run it on Power 9 as compared to Skylake kind of a system. And then in order to come on to that particular conclusion, we have identified a workload which was coming from MongoDB's website, and is a geospatial kind of a data set. And then which was a CPU-intensive workload. I'll come down to the basics and then on why it is a CPU-intensive kind of a workload. And it was loosely based on the mean stack. Mean stack, if you're not aware, is based on MongoDB, Enterprise JS, AngularJS, and Node.js. We were just making use of MongoDB Enterprise binaries, AngularJS, and Node.js over here. And then we defined service level agreements in order to evaluate the metrics associated for this performance case study. One of the SLA was to make sure the transaction response time was always less than 999 milliseconds. If you have 100 transactions, and if any of those transaction responses were less or greater than 999 milliseconds, they were qualified as erroneous, and we didn't categorize it in order to evaluate if the workload was going good or not. And then also we had another metric system wherein we said, hey, if 1% of the whole workload is greater than, has a response time more than 999 milliseconds, we just discarded that workload. It was unfit. This was our in-house metric system that we developed in order to evaluate the price performance number as such. And then the whole intent was to pack as many containers as possible on a host basis. As an analogy, you can think if you have multiple developers who need an isolated environment, and then how many such developers can you accommodate onto one system? With containerization kind of a technology, you could do that same thing. And if you can map it down to here, the intent of packing as many containers as possible was to see if you can give an isolated development environment to respective developers or testers as such. And then we worked our way through the performance per core basis, and we have the numbers. I'll probably showcase you on how the TPS and how the cores per core mattered for us. Yeah, this is a busy chart, but I'll try summarizing it into easier analogy. If you pick up your mobile phones and start searching for your restaurants in a particular neighborhood or your neighborhood, what would you probably need is two data sets. One of them is neighborhood data set and restaurant data set. This was all coming from geospatial data set, part of your MongoDB sample tutorial as it is. And then we have multiple users been doing the search operation, and it was been simulated making use of JMeter kind of a service, wherein whenever a user picks up his mobile and says, hey, give me some results back, it translates it to 5 different transactions, as you can see. So if you have 4 users doing 100 such loop transactions, it narrows down to 2,000 kind of transactions over here in a net. On an average, a short run was somewhere coming around 8 to 10 minutes long, and then the long runs, which were the benchmarking runs, came somewhere around 30 minutes long. In this particular exercise, or the performance case study that we have taken up, the software stack which we considered for evaluation of this particular performance run was in this manner. The hypervisor used on the Power 9 processor family was Power VM. That's our in-house partitioning tool, in-house partitioning hypervisor. And the industry standard KVM on an x86 machine. The OpenShift Container Platform was around 3.11, and it was remaining same. And then for you to run 3.11, you need to have RHEL 7.6, which is the latest and the greatest as of today. As of yesterday, I think 7.7 got released, and 8 also got released. And then the kernel that was coming in from 7.6 was 3.10, which was fairly the same across P9 processor and x86 processor. The intent of sticking with CentOS as a container-based OS was we were making use of enterprise DB, MongoDB of version 4.2, which was coming in handy, and hence we picked it up accordingly. And the Node.js, which was the front end based, and it was serving as a REST server, was version 8.14. Yeah, this is a fairly apple-to-apple comparison, as you can see. The systems under test, or the architecture that we resorted to, was like this. You can see the blue box, and we can see the yellow box in the slide. So OpenShift does not yet support the heterogeneous coexistence. It doesn't mean that we haven't tested. We have tested, and we got the similar numbers. But the reason we resorted to different pure clusters was to make sure when we come up with the performance numbers, it remained fairly the same. And then hence, we resorted to two different pure power cluster and pure Intel cluster. We have had the same load generator, which is based on Power 8 processor family, SA22LC box, which was generating the load and was going to the switch, which was the top of the rack switch, GA2460. And it was redirecting the flow to the respective clusters based on the URL that gets formed when it comes to the OpenShift OCP router kind of a mechanism. And you can see we have a Power VM-based hypervisor. It was running on top of an L922 box, and this was a partitioning software, and on top of which we have hosted LPAR, 2 LPARs, which is a standard terminology, which were acting up as compute node 1 and compute node 2. Then coming to the yellow box, which is our Intel-only box, we have had the KVM as a hypervisor, and we see VM1 and 2 running as they're running the operating system, and we're hosting the Node.js and MongoDB containers. And they were acting as the compute nodes in this cluster. This is more of the data flow that we have into consideration. So again, if we divide the slide into two vertical halves, on the left side of the slide, on my left hand of the slide, we can see the pure power-only cluster. The load is getting generated, or the simulation of the users are getting generated from the JMeter box. It gets routed through OCP route kind of a mechanism, which is our ingress controller. And then it distributes the load to your LPAS hosting your containers. The small rectangular block boxes that you see here are nothing but the container representation of how they are running. It gets evenly distributed across onto both the systems. And because we have a unique URL, we are able to target which particular host does the generator is going to hit is being expressed over here. And then we go to the next half of the slide, wherein we have had the Intel-only cluster, which is a Skylake cluster in the comparison that we have taken. And then again, we have the OCP route kind of a mechanism, which is our ingress controller. And it helps redirect the flow based on the URL that gets exposed and is on top of your OCP router, and it redirects it to the respective MongoDB and Node.js-based containers in this equation. When we narrowed it to how the MongoDB container was looking at when it comes to the performance comparison, as you can see, the Intel Xeon SP-based 6150 box was premature in terms of the number of containers being hosted on top of it. We see there were 98 containers that were hosted on top of it, which means that was across a 36-core box, and it was evenly distributed across 2 VMs. So if you take the number of TPS, we are coming down somewhere around 2,200 or 2,300. When we do per core comparison, which is how many containers can the Intel Skylake box can accommodate, we can see it is somewhere around to 2.7 containers per core. When it comes to Power server, Power 9 base server, we can see it is somewhere around 8.7 containers per core. When it translates, net, we see 3.2 greater container capability per core as such. You would probably think what a container is. Just a container can be thought of as a lightweight operating system, which helps you pack all of your binaries and libraries onto it. Then the moment you spin up those containers, you have the application runtime available and could be leveraged for your application development as such. So this is a configurable compute unit. How can you configure it? So we have a few label identifiers, or few identifiers by which you can configure this compute units. One of them is labels. If you have the label mentioning it as, whenever I spin up a container, it should go and sit on top of an AC922 kind of a box, you can label it accordingly. And then when it comes down to the CPU, memory, and the storage units, you can also configure and tell, hey, you cannot give more than 2 CPUs or virtual CPUs to this box. And then same goes to your I/O and your storage as well. Speaking of data-intensive workload that we have had as an objective, the another CPU-intensive kind of or data-intensive kind of workload that one could target is your AI models. I will not dwell much into this slide, but with AC922 kind of a workload as a server of choice, you could do large model support. As an analogy, you can think of processing your high-resolution images on top of your GPUs. It will always go into out-of-memory kind of an exception kind of a thing. With cafes, libraries, we could offload the relevant pieces of processing onto your CPUs, so you don't overshoot your memory, and you can come back and leverage the same data accordingly. With PCIe Gen 4 kind of a thing, you could pump in the data back at much faster rate as compared to any other PCIe Gen 3 kind of a model supports. We have distributed deep learning, wherein the understanding is the convergence or the rate at which you learn or the model learns is done at a much faster level. And then we have the industry standard NVLink 2.0 in place. So these were few in-house testing that we have done, and we realized that Caffe was doing near about 4 times much better as compared to the Intel GPU boxes in the picture. As a net, if I put this up in a visual representation on how in today's Power cloud model, what we can do better over here is when it comes to the MongoDB as a performance case study that we have taken, we realized that we are doing 3.2 container density on a cloud kind of an environment, and then when it comes to the price performance ratio, we are doing 2.x kind of a thing. And then with AI modeling kind of in picture, we are doing 4x much better as compared to Intel Xeon V100 GPUs. And then the in-house testing that we have done was with Caffe and the large model support, and we have done the iterations near about 1,000 times, and then we concluded that a workload which was taking 3.1 hours on Intel was fairly doing in 49 minutes on a Power server. Power is already a part of open hardware kind of an ecosystem. With Red Hat in picture, we are also have provided the software enablement option, and then with which we give the openness and the choice of what kind of software can run on what kind of hardware is left to the ISVs or the business partners. As a summary, I would like to give you some few takeaways over here. The performance on a core basis, as we have compared, is pretty high. The reason it is pretty high is we have a huge footprint. When we visualize the same on planar surface of your hardware, your memory is residing immediately next to your cores, which means the response time, which considerably comes back in pretty less time, and hence we are getting a higher throughput. And then when it boils down to how many dollars could be invested on a container basis, it already speaks to us, and it has a 2.6 much better bandwidth on a 20-core Power-only box as compared to Intel-only box. I have a canned demo, which I would like to give. So this is a 3.11 OpenShift cluster running on top of Power Server. I logged in as a default user system admin. And in this cluster, I have had one management node and two compute nodes. One of them is scheduling is disabled. I mean, we were doing a few internal testings, and we wanted to do and see if we can attain the same number of container capacity on the same system, and hence we disabled this. This is a PP64LE box, Little Indian version of Power processor. This is, as I mentioned in my architecture previously, this is a Power 8-based master node. We can create as many projects as we can. When it comes to the Kubernetes terminology, which means name spacing convention, so we see there is something called as Mithun 1. This is the project that we have taken, and then this is the way we can isolate our projects. We can have multiple such projects existing on the same OpenShift cluster. This is a fairly new project, and we see nothing has been running on top of them as of now. We were making use of the Helm approach to see the ease with which we can shift and translate towards OpenShift from any Kubernetes kind of platform. As of now, there are no parts or containers running at this point, and I have deployed an instance with reference as Harsha, and then we can see how the parts are coming up. So it takes instantly to deploy or pull the respective Docker images from the registry of the OpenShift and then see how it comes up. You can see there is a route which has been created. This is our external route. So this can be used for our external accesses. If you have any APIs been coming up, we can see if it comes up or not. It's going to take a little while. I probably should be doing some updates over here. So I can describe these parts and see how it is coming and where it is getting deployed at. If you can see at the node name, it says it got deployed onto 133 hosts, which is the only host in this point which is schedulable. And then I'll probably try reloading it, and it comes back again. I will probably try logging into one of the nodes to see if it got scheduled properly onto it. There are multiple such parts over there in place, and all of them translates it to different projects that I have on the system. So as I was mentioning earlier, when it came down to, we have 256 GB of memory being shared across two VMs, and it was running in SMT8 mode, and this particular box had 128 GB with it. This is our JMeter box, and it is running in Power 8 mode. It was fairly used for generating the workload over here. You can see the transaction response time is somewhere around 999 milliseconds, and the URL that we have used is unique, and this is how we were trying to target each and every particular OpenShift cluster. I would probably not dwell much into this on how it is going and how it is being translated over here, but that was it, guys. Thank you. If you had any questions, please let me know. Sure.
Why are the containers deployed in virtual machines? Why is it not deployed on the bare metal itself? Is there a reason for that?
No particular reason.
Okay,
Okay, my question was, why did you use virtual machines to deploy the containers instead of
Not the bare
deploying
metal
it
mode.
directly on the bare
So
metal?
so when we're doing a comparison study, we also had done a single node testing, as you have mentioned. The numbers came exponentially way better as compared to Skylake, and we wanted to test it on a virtualized container environment. Because if you host on a cloud, not everyone will resort to a bare metal approach over there. We were trying to replicate the cloud scenario. Not everyone will try to resort to a bare metal kind of an approach over there. And hence, we wanted to do a virtual machine over there, because when it comes down to cloud terminologies, it is a virtual machine as compared to bare metal. We tested it over there, and it came fairly good in terms of the performance comparison. We have also done a bare metal kind of an approach too. And if I'm not wrong, we would able to scale somewhere around to 240 containers on one single machine. And it was just on a Power 9 server. And if it came down to Skylake, it was somewhere around 100. So we are still in the preliminary testing phase over in the bare metal mode, but the numbers are looking pretty favorable in terms of power processor.
One more question, please. If a container is running on a system with GPUs,
Okay.
can it use the GPU resources?
So what exactly is running inside your container? Is it the data that it is hosting, or is it? And then to answer in a simpler way, yes, you can allocate a device to your container. When you can allocate a device, you can always allocate a GPU to your container also. So the other way of thinking is you could containerize your machine learning and deep learning model also, because it will have a lot of software libraries dependencies, and you cannot spin it up again and again. So you could do that also, yes. Sure, thank you. Thank you, guys.